Done. Okay, so you can follow along in your booklets. There's going to be a few gaps. Okay, that was the first slide that we looked at. We've had a look at what causes a tsunami, an earthquake, an underwater earthquake. You can have an underwater landslide that does the same thing. And I know there's this particular island, I can never remember the name of it, but a huge piece of that is going to fall off at some stage. And then it's going to send a tidal wave, a massive tidal wave, and that will cross oceans. Yes?
What's the picture on the plate tectonics?
Let's just work through.
That's the magma.
Let's just work through.
Where's the tsunami going to go?
Okay.
I think it crosses the Pacific Ocean. I'm not sure. I'd really have to look that one up. Here are your key learning intentions. Recognise major plates on a world map and know what a plate is, of course. Relate the occurrence of earthquakes and volcanic activity to plate boundaries. Again, we have to talk about plates. Model seafloor spreading to consider the role of heat energy and convection currents in the movement of tectonic plates, and be able to relate the extreme age of stability of a large part of the Australian continent to its plate tectonic history. If you look at this little diagram here, you can see, oh yes, all of the continents pressed together, Australia down there, and these arrows of force, slowly but surely, over a period of time. This is 40, 30, 20, so you've got your time counting down, present day. So 200 million years ago, 180, 170, so they fit together like a big jigsaw puzzle. And remember that jigsaw puzzle idea, because that's one of the pieces of evidence that Wegener put forward, that the continents were once together. He said they seem to fit together like a big jigsaw. Okay, and he thought that can't be a coincidence. So you'll see there, Australia was nudged against Antarctica at one stage.
More land came.
India just got caught by Asia.
Yeah, India just got snapped up. So let's have a look at this. You need to understand the following testable terms. What is a tsunami, Pangea, continental drift? Wegener's 5 types of evidence for continental drift. Okay. Then what Harry Hess did, seafloor spreading, magnetic striping, and sediment thickness. So Harry Hess had an extension on Wegener's theory. Wegener had these 5 key ideas for what was going on. Okay, tsunami. There you go, huge ocean wave caused by an earthquake on the sea floor. Did I leave a gap there? Fill in tsunami. Remember, for my slideshows, if it's red, it's examinable. Okay, there's a gap in that booklet, on that page, fill that in. Okay.
Let's go in.
I'm about to fill it.
It's not a complete booklet. How is a tsunami formed? And there you go. You've got that little bit of rise underwater, and you get a bit of a wave. Now, as I said, if you were in a boat on the ocean when that happened, it would be certainly survivable. But what happens to that very wide wave when it gets towards land? And you can see as the ocean, the depth decreases, the water starts to pile up and pile up and pile up. So you end up getting, because the front is moving slower than the back, so it's getting pushed up, pushed up, pushed up, pushed up, pushed up, and you end up in a situation where the wave can be considerable. And it's not as dramatic as you see on the movies when you see this big wave come through. It looks like a wall of water. That wasn't a big wall of water, but it was certainly unstoppable. It was a very wide, reasonably high wave, and it just kept coming and was unstoppable in that regard. So tsunamis are caused ultimately by earthquakes. And what causes earthquakes? Well, it's when these plates that are underneath everything shift, and we'll talk about those. Right, here's this idea that Wegener had. So in 1912 he suggested that 200 million years ago this supercontinent existed called Pangea. Okay, if you're not writing, you need to be writing. You need to fill in those booklets. Okay, the one that I gave you that you need to fill in. Continental drift is this idea of the gradual movement of continents moving across. Wrong booklet. 3 times I said this to you guys. Okay, across the Earth's surface through geological time. He reached this conclusion after looking at different types of. Do you have a booklet?
No.
Come and get one. Okay. He reached this conclusion after examining different types of evidence. The continents seem to fit together like a jigsaw. That was the first one. Okay. That was his first piece of evidence. And there's that supercontinent called Pangaea. Okay. Okay. Now, here is another slight. This is the same continent, but you've got these Pangaea splitting into Laurasia and Gondwana. Laurasia and Gondwana, and you can see that's that semi-supercontinent down there. Gondwana consists of South America, Africa, Antarctica, India, and Australia. So it gives you a better, clearer picture of Australia nudging up against India and Antarctica. Okay? Yes?
Why were they called that?
I don't know. Why not? You know, like if you're asking me what is the language that the names are derived from and the meaning, I don't know that one. Okay. So it'd be worth looking up. Yeah. And then subsequently, those two split further. Okay. Here's the second piece of evidence: coal deposits. You get coal deposits on continents that are too cold to have coal, like, for example, in the Arctic Circle. So coal comes from forests that, forest material, woody material that has dropped to the forest floor, built up over time in the sediment and formed coal. So, but, you've got these continents that are covered with ice, or these areas covered with ice. But if you dig deep enough, you find coal. And he suggested, well, at some stage, there must have been a forest there. So this continent must have been in a different location for that to happen. Then the opposite of that, these are the easy ones to remember. The opposite of that, you've got glacial scars. What's a glacier? Yep.
A huge block of ice.
Yeah, it's like a river of ice. They form in the mountains and they very slowly work their way down to the ocean. Okay, really slowly. And they leave scars because they scratch out valleys as they make their way down. They're incredibly heavy. Okay, enormous amounts of force. And so they leave. If you go out to Epilogue, if the water's very low, there's a rock out there that has glacial scars on it. You see a lot of glaciers in Australia? Like, we're a hot continent, okay, but Epilogue has glacial scars on rocks out there. So at one stage, Australia was in an area that made it significantly colder. So on the continents too warm to produce glaciers. Mountain ranges in North America and Africa seem to have been part of the same mountain range at one stage. And the same is true of Africa and South America. So you get this idea where you have these continents that were once beside each other, and mountains would go from one continent to the other. And now that they have split apart, that you think they're just separate, distinct mountain ranges. But if you line the continents up, all of a sudden the mountain ranges also line up, which would be an incredible coincidence. That down here is an example of glacial scarring. So these lines, as the glacier has moved through, and it's carrying rocks on the underside, it's just scratching out the rock that it's riding on top of. So these mountain ranges line up. This mountain range over here lines up as well. Can I change? Yeah, should be able to. You don't have many words to fill in. Now here's fossil evidence. Same idea. When you line the continents up together like a jigsaw, you get fossils on one continent of animals that used to live there. So that's the area that this animal used to live in. And that's the area that this animal used to live on this continent. Now these continents might be thousands of kilometres apart. So how did that animal get between those two continents if there's no fossils in between, if you wanted to take a route by land? And again, but if you line them up, you'll see, oh yes, in rocks of the same age, you'll find fossils of the same type, which again suggests that these continents were together at some stage. So you've got Australia, Antarctica, and the fossilised life on Antarctica is nothing like the life that exists there now, because the life that exists there now is evolved for an extremely cold continent, but the life that used to live there, ferns, you don't find there now, and would not survive there now. And these particular ferns, you'll find fossils for them here, and in rocks of the same age in Australia, all the way through these ranges. So that's compelling evidence again. You don't need to know the names of the organisms that made the fossils, but you will need to know at least 3 pieces of evidence that Wegener produced. So what are the 3 pieces of easiest evidence to remember? Jigsaw would be one, glacier would be the other, coal would be the third. Coal were on continents that are too cold to have forests, glacial scars on continents too warm to have glaciers, and the continents seem to fit together like a big jigsaw. Okay, and then you've got the last two. So you need to remember at least 3 of those. Any questions at this stage? No? Okay. There's the 6th one, magnetic rocks. Now what does this mean? When new rocks are formed from magma, magnetic minerals in the form of magnetite align with the north and south poles. So you get a volcanic eruption, and some of the minerals in that rock, in the liquid lava, are going to line up like a compass needle. They're going to point north-south, and then the rock is going to set hard. The lava will set hard into a volcanic rock, and those minerals will all be pointing north-south. But what happens if the rock or the entire island moves and turns to the side? Now the north-south pointing minerals are not pointing in the right direction anymore. And that's what's happened here. When this lava rock was formed, north was actually north is always up in this example. But this lava mineral was formed, the mineral was pointing the right way, but then the whole continent turned. This continent turned a little bit, this continent has turned a little bit to the left, but when you fit them together like a big jigsaw puzzle again, and you line up the minerals in a north-south fashion, the edges line up pretty neatly, and the minerals all point towards magnetic north. And that's the 6th piece of evidence that Wegener had. That when you go and visit different continents and look at magnetic rocks, which way the minerals are pointing in the north, a lot of them are not pointing towards the north. And when you reorient the whole continent to resolve that, you find out, oh, again, everything points the right way, all the edges line up neatly, and you've got yourself a supercontinent. Yes?
How's the mineral point somewhere again?
How do magnets point north?
Well, they turn.
Yeah, they orient themselves north-south, yes?
Yeah.
I'm not saying the mineral orient, I'm saying that when it erupts as lava, so it's liquid rock, yes?
Yep.
So have you ever magnetised a needle? Take a needle, rub it on your clothes, and then sit it on maybe a leaf floating on water, and the whole thing will turn to go north-south.
Okay.
Yeah? And it can do that because it's responding to the magnetic field of the Earth. Yeah? And that's what these minerals do in liquid rock, in lava. So as it erupts, the minerals will all just start to face north-south, like a needle, a magnetised needle, and then the rock will harden and everything is locked in place. Yes?
But like don't magnets like change over time to
The magnetic fields,
yeah.
and that becomes really important later. Yes, yeah. So you have to take that into account, and that has been taken into account. But yeah, the Earth's magnetic fields do flip, and that becomes really important as key evidence as well later on. You'll see that for rift events. Okay. Now, no one believed Wegener. This was 1912. So think about that. That's not that long ago. It's a little over a century ago. So plate tectonics as a science is really young. And no one believed Wegener. He had these 6 pieces of evidence he thought were pretty good. But, okay, fine. You're arguing that the continents move. How the heck does something the size of a continent move? Like, what force can drive a continent? You're not going to have strong winds or water pressure or something like that doing it. So it was inconceivable to people that continents could move. But just because you don't understand something doesn't mean it's not true. Now, World War II happened, and during World War II, really comprehensive maps needed to be made of the ocean floors for the purposes of fighting that war. Submarines were developed and things like that. And they found a few things. They found these big volcanic mid-ocean ridges running down the middle of oceans. Huge. Okay? They also found these incredibly deep trenches, up to 11 kilometres deep, which was again very odd. Everyone just thought that the bottom of the ocean is going to be like the bottom of a lake bed. It's going to be pretty smooth. It's going to be deep, but it's going to be pretty smooth. And they get down there and you've got these incredible mountain ranges, much bigger than anything you see on land. Okay? The ages of the rocks on the ocean floor vary from brand new to about 200 million years. So the rocks vary in a regular pattern in age, which seemed odd. Magnetic ocean floor rocks have magnetic stripes that actually parallel the underwater ridges. which seemed really weird. And we'll talk about what magnetic stripes are. And the stripes show the youngest rock is right next to these ridges. So right next to these huge ridges in the middle of the ocean, you have very young rocks. And then as you get further away, the rocks are older and older and older and older. Can anyone think of a reason why that might be? Why you get young rocks right beside this mid-ocean ridge? So here's the middle of the ocean. You've got the youngest rocks possible right there. And then as you go away, older, 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 older. Yep.
The lava forms
Yeah.
first, it extends,
And then if you're thinking new rocks are being formed at the edges, and then the rocks are being pushed away from the trench or the mid-ocean ridge, that is what's happening. It's working like an enormous conveyor belt. Harry Hess, this is the second important guy, 1962, so about 50 years later, suggested the rocky crust was formed at mid-ocean ridges and spreading outwards. So what he was saying is new rock is forming at these mid-ocean ridges and it's spreading outwards. See how the arrows are moving away? And that's why on this particular picture, let's just put 200 over here, million years. I'm going to put 200 million years old for that rock, and I'm just going to put 1 year old for that rock. So actually fill that in on your diagram. So the rocks are going from young to old, and the same that way, young to old. So you need to fill that in on your sheet. Okay, and then now we've got these weird little north-south symbols. Let's talk about that. Okay, so what evidence did he provide for this? The age of the seafloor. Youngest rocks are near the edges and they get pushed away. So that was his attempt to explain this observation that people have made about rock ages. Then magnetic striping. Patterns of magnetism trapped in rocks on each side of the plate boundaries. Now what does this mean? We just talked about magnetic minerals. When the lava comes out, all the minerals line up north-south. Yes? Every so often, every few million years, the north and the south, the magnetic field of the Earth flips. So when that happens, we in Australia will live in the northern hemisphere. The South Pole, as we understand Antarctica, all compasses will then face that because it will now be north. Do you understand that idea?
Yep.
Yeah?
How often does that happen?
I can't remember the time periods. It's millions upon or tens of millions of years, and it's a little bit unpredictable, but broadly predictable. But you're not going to say Tuesday in the year 2197. It's going to flip.
There'd be 52 Tuesdays there, wouldn't there?
Yeah, no, but you understand the point I'm making. It's not specific. Like it sort of goes. Oh yeah, it's every few million years, and when it does happen, it happens fast. Yes.
So, in that time, would that mean that maps would be flipped because the northern...
The maps would still be accurate, but north would then be pointing to the bottom of the map.
Yeah.
But all the continents relative to each other would be right. It's going to mess with animals. Anything that navigates using the magnetic field.
But wouldn't it also be a little bit confusing for humans? Sort of?
Oh yeah, but we'll know. Like we'll be able to consciously process that. Like and GPS doesn't worry about that either. GPS is using satellites to locate position. Okay. So now, why is this important for us? Okay, let's have a look at this rock here. When this rock is being formed, our very young rock, north is down here. Okay. And so all of the minerals point that way. So the new rock, when it was formed, all of the magnetic minerals are pointing towards the north. Yeah? Now, when this rock over here was formed, north was that way. That shows that the north-south pole had flipped on the Earth. When this rock over here was formed, north was again that way. When this was formed, north was that way. So you can see these periods where the Earth's poles flipped from north to south, they flipped around, and any rock formed at that time, the minerals would point towards wherever the magnetic north was at that time. And you mentioned that before about the flipping of the poles. This is again strong evidence for seafloor spreading. See, these stripes are moving away from the trench again. Okay, these rocks they weren't formed at the same time. Their ages show that they're the youngest are nearest the trench, the oldest are here, and this flipping that you see here, this magnetic striping, is a reflection of where the north and the south poles were relative to when these rocks were formed. Now the last one is sediment thickness. Over here, on the oldest rocks, the sediment is very thick. And over here, I can't take that, that's probably my physiotherapist. Over here, I've put my back out. So over here, the sediment, there's really no sediment. There's no sandiness on these rocks, they're just bare volcanic rocks. And so that again indicates that these rocks here are considerably older than these rocks here. So far what we've looked at, there are 6 pieces of evidence from Wegener for continental drift, and there are 3 pieces of evidence for seafloor spreading, which is related to Harry Hess. Any questions? Yeah?
Can we go back to the slide where it has those substances?
Yeah, we can in a second. I'll do that at the end. Any questions specific about this and these pieces of evidence here? We'll be doing some worksheets. We'll probably get a little video in and things like that. Okay, but that's the way things are going now. I hope everyone's filled in their diagram. Okay.
Did you have
Now-
to add everything?
Sorry?
Did you have to add everything that you just drew?
Yes,
All
you
the
did.
Arrows?
Yep, that would have been good.
Ah,
Now, there is revision. 1, 2, 3, 4, 5, 6. That makes a pretty good cram card. What do you see in the top right corner? Let us see. Cram card. I'm not very imaginative. Okay? You should be able to explain each of those things and continental drift. Each of those things and seafloor spreading to fulfill that requirement for the key learning intention. Theories of Wegener and Harry Hess are supported by various pieces of evidence, but neither scientist could explain something or how something as huge as a continent could move. You can, you've done year 8 science, but they couldn't. Okay? Yes, you did year 8. Sorry?
Year 9 science.
No, year 8.
Where did we learn that in year 8?
Oh, you didn't do convection currents in year 8?
Oh, no.
You didn't talk about heaters, the hot air going up,
Yes, we
then
did.
going
Yeah,
across
yeah,
the
yeah,
earth,
yeah,
going
we did.
down. This business.
Maybe they
Yeah, we
right.
did.
For like 10
Oh.
seconds.